Welcome to Black Hat Briefings, held November 21st through the 22nd, 2001 in Amsterdam. This is videotape number 2, third generation exploits on NTWin2k platforms.
Right, I think I'm scheduled to start now. My name's Halvar. I'm a reverse engineer for Black Hat Consulting. And I'm going to speak about third generation exploits. That's pretty much it. There are a few basic rules when I speak, which basically include I'm just the speaker, you're the person who's trying to get something out of the speech. So whenever I speak too quickly or a speech slurred or I'm not making myself clear, yell at me. And if there's any question in the middle of the speech, just raise your hand, or if you don't feel like raising your hand, just ask right away. Okay, I'm a bit nervous about this because I haven't held the speech before, and those who have seen one of my previous speeches probably remember the previous speech to go rather smooth. And I can assure you this one won't go very smoothly. So, all right, we're in for quite a ride. The speech consists of two rather large halves of 1¼ hour. And during the first half, I'll cover a quick recapitulation of the first generation exploits. I'll not really go into them deeply, as everybody knows about these. I'll speak a bit about second generation exploits. I'll not go too deeply into those either because they've been documented somewhere. Then I'll start speaking about third generation exploits and what's different about them, why they're important, and, well, yeah, how to take advantage of those. And then I'll speak about the first component of third generation exploits, which is heap structure exploitation. Basically, it's buffer overruns in mallocked buffers. And I'll specifically focus on the NT side here because the Unix side has been documented in the last frac by Max from Synergy. And as far as I know, nobody has ever documented how this works under NT or with NT compilers and so on. So I'll speak a bit about that. I'll start with some heap management generalities because you need to have at least basic understanding on what a heap manager is, how it works, and so on. Then I'll speak specifically about exploiting buffer overruns under the Win2k heap manager. I'll have a short demonstration concerning this. Then I'll speak specifically about how to exploit these malloc overruns in the ball and C heap manager, and have a demonstration concerning that as well. And finally, I'll speak a bit about the future of exploitation because the field of exploiting buffer overruns is going to change drastically within the next few years, especially with new CPUs like the IA64 coming in, and things like non-executable heap and stack pages being a standard feature, and the fact that you'll most likely not be able to execute shellcode anymore in a year from now or in 2 years from now. So the entire way how buffer overruns will be exploited will change a bit. Then we'll all take a well-deserved break, especially I'll need one. And the second half is going to recapitulate on how to exploit format string bugs in the beginning. I think everybody's pretty familiar with it, but just to have a common level of understanding in the audience, I'll go quickly over it. I'll speak about the history of format string bugs. I'll speak about the automated detection of format string bugs. And I'll speak about exploitation of format string bugs. And then the core of the second half will run around, which is exploitation reliability. We all know that it's quite hard to exploit reliably in the wild. I mean, it's always easy to write an exploit that works in the lab, but if you actually go out there and want to own boxes, you need exploits that have a pretty high probability of getting in there, and getting in there without knocking over the service too many times so the admin doesn't notice. I mean, stupid admins will usually restart the service 3 or 4 times before they actually notice something fishy is going on, but still it's nicer if you can just walk in there without leaving traces. I'll define the problem of exploitation reliability later on. Then I'll present something you can do under NT, which will give you a very, very high probability of getting control without messing with the stack in any way, which is called the unhandled exception filter attack, which is nice for lab environment, but only really good if you know very much about the attacked system. And then I'll speak about the threat environment structure override, which is something I've invented, which works very well if you know pretty much nothing about the target box beside it's an NT machine. So we'll get into that later. And afterwards, I'll have some free time for questions, answers, and discussions. And if your head isn't hurting too much, I think I'll come up with something else to speak about later on if we still have time. Okay. Any questions concerning this? No? We all know first generation exploits. Those are the standard stack smashes where somebody's copying data into a stack buffer and smashes the EIP, or the instruction pointer, which has been saved on the stack. In this nice diagram, you have the local variables of a function in green. You have the saved frame pointer in what I'd call a light blue. And you have the return address in red. And somebody starts copying lots of data into this buffer and just completely overwrites all the data that's behind your original buffer. And when the function that smashed the stack returns, it will read the user-supplied return address from the stack. And therefore, the attacker can point the instruction pointer to any location in memory where he has put his shellcode and execute that shellcode. I think this is pretty basic and common knowledge amongst everybody. So first generation exploits are the simple stack smashes. They've been documented in about 1 million documents, a few very good ones by LF1, and then a few very bad ones recently because everybody thinks to need to document it once more. The EIP is completely taken, so we're taking advantage of a hardware-specific feature. We're exploiting the functionality of the return instruction, which reads the return address from the stack. We're fairly low level at that point, so this is very CPU-specific. I mean, it happens on many CPUs, but still it's very CPU-specific. The usual way these bugs occur are the basic calls everybody knows: string copy, gets, sprintf, the top 3 on every grep list when you're looking in source code. And they're fairly trivial to exploit. I mean, you just point the instruction pointer somewhere useful and then execute code there. They can be a bit trickier to exploit if the input is filtered, like if you only have uppercase characters from A to C. It's going to be tricky to exploit it. But unless the input is very heavily filtered, it's usually no problem. I mean, there's shellcodes around which only consists of A to Z, 0 to 9, and so on, at least on x86. These kind of bugs can be detected via stress testing. You just fire long strings into an application and hope it'll fall. And there'll usually be a seg fault when you overwrite EIP completely. So everybody has played with Perl scripts, I assume, or EI's Elite security scanner with the same artificial intelligence to find buffer overruns as Perl has. Anyways, due to the easy-to-find nature and the easy way to exploit these bugs, they're almost extinct in open source software. It's a bit like a biological analogy. You have beautiful animals out in the woods. It can be spotted, and it gets a high value on the market. So people will hunt it, and in open source, they've been pretty much hunted to extinction. They're still around somewhere hiding in the closed source woods, but I don't think you'll find too many of these days. Whoops. Then there's second generation exploits, which are a tad more complex. There are cast screw-ups and off-by-ones, which occur from, oh, I told you this was not going to be smooth. Which occur from misusage of so-called safe functions like strncat, strncopy, and so on. They are fairly well documented. There are FRAC articles on exploiting off-by-ones. In this case, you do normally not overwrite EIP, as you only write 1 null byte past the end of the original buffer. And therefore, you don't take advantage of a hardware-specific feature such as the return instruction, but you take advantage of compiler functionality. You're basically exploiting the standard C prologue and epilogue of a function. I'll explain how this actually gets exploited in the wild in a minute. These ones can be quite hard to detect, as there are a few very subtle things that can happen. For example, if you define a char buffer with 20 bytes, and you access the 20th element of that buffer, like buff square bracket 20, you're not in that buffer anymore, because the buffer starts at 0 and ends at 19. So a lot of these things are a bit tricky in the C language. So they are a bit tricky to detect, and they cannot be automatically detected. Secondly, you take control after a small detour. You don't immediately take control by overriding the stack. You take control by manipulating a compiler internal variable, the frame pointer, and then taking control afterwards after you've manipulated this. So a few of these can still be found. I mean, well, pretty much all exploits that have been posted recently somewhere are off by ones or similar subtle bugs. Now, the way to exploit these is a bit tricky. We have the buffer to which we append in blue here, and we have the saved frame pointer in white, and we have the saved EIP in red. Now, the frame pointer is used by the compiler to index into local variables. So when we write a null byte behind our original buffer, the terminating null byte for our buffer, we override the saved frame pointer's lowest byte with a null. Therefore, we decrease its value. Now, my diagram is upside down to a certain extent because the stack goes top to bottom instead of bottom to top. In this diagram, it's inverted, but doesn't really matter. So the saved EBP is manipulated, and when the function which smashed the stack at that point returns, it executes the standard C function epilogue, which is move ESP EBP to erase local variables, and then pop EBP, which pops the manipulated frame pointer into the EBP register. Then the function returns as usual, and nothing great happens. We just have to keep in mind that we've manipulated the frame pointer to point elsewhere. Now the next function, the calling function, returns as well. And the calling function executes the same code, move ESP EBP. Now, as we've manipulated EBP to be decreased, it would slide downwards in memory and in this diagram upwards. So the ESP slides upwards from saved EBP where it should point into the user supplied data. And when the program then executes the return instruction, it takes the data instead of out of saved EIP out of the user supplied data. This is where the attacker gets full control and can point the instruction pointer to any location he wishes. Any questions on this? Okay. Then there's this third generation, which is basically split up into two variants. First off, there's format string bugs. It's a new bug class that was discovered in summer 2000. I mean, I think we all remember the day when that TF8 exploit for Woo FTPD hit bugtrack, and a bunch of people were trying to figure out what exactly it was doing. It seems that this class of bug has been around for a few years in the hands of a few people who didn't give it out. And that means that these few people had general keys to any computer in the world for a few years. Nice. Okay, these bugs come from a misuse of the printf family of functions, where people don't actually supply a format string like %s, but they just pass the user supplied data as format string. Nothing happens as long as the user doesn't put a % in there. They are fairly trivial to spot. They're probably the only bug class that can be spotted completely automatically. And they're fairly well documented by now and widely exploited. After the first exploited bug track, there was like an entire wagon load of exploits hitting the mailing list within the next few weeks. I mean, everything was vulnerable, but due to the easy-to-find nature of these bugs, they were very quickly hunted to extinction almost. The funny thing about format strings is that you don't really smash anything which gets you direct control. It just allows you to write to an arbitrary address or read data from an arbitrary address if the output is echoed back to you. So you don't overwrite any CPU registers directly, and you're not exactly taking advantage of a CPU-specific feature at all. You're taking advantage of something that has been documented and is standard and was there in the ANSI ISO-C specification. So basically, we're moving away from the hardware to a higher abstraction level when it comes to the to new generation of exploits. The lowest level has been exploited, the return instruction. Then there's a higher level, which is the compiler functionality, the frame pointer overrides, which have been exploited. And now we're moving a bit higher to the level where we are dealing with standard functionality in the libc, which nobody has ever thought about before. I mean, it's there. Nobody reads the specification. Did any one of you know there is a %n in printf? I didn't. So anyways, these bugs are very simple to exploit. They're very powerful, and they're very easy to find, which is a property that is not very good for the bugs because they're hunted to extinction very quickly. you have to imagine that format string bugs are pretty much very, very beautiful bugs with very shiny shells, and they're very, very trivial to spot, and they're very valuable. You can imagine that they won't last long. I doubt you'll find any high-profile format string bugs in any open source application these days, because everybody has a tool that scans for format string bugs, and about a week after the WooFTPD exploit hit, they're just running those tools over entire code trees. And you might still find a few of them in closed source software, but it's getting fewer and fewer. I mean, even Checkpoint cleaned up all the remotely exploitable ones. Yeah, that took quite a while. Oh well. They claim to have a tool to find these things. They claimed that before too, but now they're actually gone. Okay. The second half of third generation exploits is heap structure overrides. Most programmers or many security researchers thought that an overflown malloc buffer is not dangerous unless there's data behind that malloc buffer used by the program that can be manipulated to gain access or gain raised privileges. Solar Designer was the first to publicly document that you can actually override the control structures that the malloc and free algorithms use to write to arbitrary addresses under most Unixes. There was in a post on Bugtrack, I think, or vulndev concerning an exploit for a trace route. These kind of exploits take advantage of the libc-specific implementations for malloc and free. Basically, they're even more abstract than generation 1 and 2, and they're way less standardized than the format string bugs. Format strings are in the standard. Every compiler has to implement them in the same way. The malloc and free algorithm just has to work transparently to the programmer, but there's no standard on how to implement it. There's a wide variance or variation between free and malloc and free algos. There's heaps of them out there, and they're all subtly different, and you need to know the exact algorithm in order to exploit this properly. So there's a lot of work to be done, and if you enjoy reading source code or binary, then there's something you can do in your free time. They allow writing to arbitrary addresses, arbitrary data, and they've been documented for Unix in FRAC57, as I mentioned before, and up until today they are undocumented for NT. And they're very hard to detect via stress testing, if not impossible. Because depending on the malloc algorithm used, you need specific data to override that heap structure with in order for anything useful to trigger. Now, if you just override it with straight A's or straight Z's or straight numbers or whatever, nothing will happen, as you have to manipulate the internal logic of the free algorithm in order to do anything useful. So without knowing the exact algorithm used, you can't really know what you should write to the end of the buffer. Furthermore, with stress testing, you never know how large the original buffer is. So you're probably shifting around by a byte or two, and you're not overriding or writing the right bits into the right locations in the control structure. So most likely, the heaps and heaps of malloc overrides in closed source software, and nobody's ever found them because nobody knew how to look for them. Unless you're reading the binary, which only a handful of people do, you're not going to get anywhere. Furthermore, most or many of the malloc free handlers use exception handling, at least under NT. So even if an exception occurs by luck, they handle it themselves and return a failure for the free call. Have you ever seen a programmer check for the right return value of a free call? No. So these ones are still around, and they will be still around for the next few years, I assume. They're here to stay. Any questions so far? Right. First off, before we start getting into the abusing, we have to get into the abstract architecture of heap managers. There's quite a lot of different algos around. I mentioned that before. Every compiler, and thus every libc, supplies its own algorithm pretty much for heap management. And if you want to have just an estimate on how many algorithms are out there, has anyone written or read Ranhelia's book on Unix internals, like Unix internals and New Frontiers or whatever? I mean, it has a fairly extensive chapter on kernel memory allocators. And that book lists 8 different kernel memory allocation algorithms just for kernel memory. Now you can assume that if there's 8 different algorithms on various Unixes just for kernel memory allocation, that the variety of kernel memory or of memory allocators in total is going to be huge. Secondly, many programmers are being taught in optimization classes that they're supposed to create an allocation profile of their application, like to see what size of buffers it allocates frequently, and then optimize the heap management towards that. So they supply their own heap management algorithms. If you look at any large application like Netscape Enterprise Server or Oracle, they have their own heap managers in there with their own specific control structures, and they're not documented anywhere, so unless you take it apart and read the disassembly, you will not know what to do. And thirdly, many operating systems supply their own. So on NT, you have the entire heap management API supplied by the kernel as well. Or not by the kernel, but by the Win32 API. So there's 3 major branches of heap managers in any application. I even have created a nice spiffy diagram. I doubt I'll make it any clearer if I try to explain what's actually going on there. Is there any question concerning this? No? I'll quickly go over it. On the far right, you have the NT heap memory API, which is the heap alloc, local alloc, global alloc function calls, whatever, which are used to which can be used to access the Windows 32 heap. And those chain through to the virtual memory API to allocate pages and then chop off small chunks of that pages and dish them out. Now an application can either call those directly with the arrow on the far right, over there, or they can use their own libc, like the compiler they use supplies their own libc malloc, which either uses the virtual memory API directly or uses the NT heap API, thus the 2 dashed lines. And then there might be a customized heap implementation inside the application, which either calls the virtual memory API directly or calls the libc heap management API. And to be honest, there's one error missing. It could also call the NT heap management API. So things can get quite complex here. And you have to remember a lot of weird structures and start documenting as many compilers as possible. Okay, for the Win2k heap manager, we have 3 major functions which are used: local alloc, heap alloc, and global alloc. And basically, local alloc, global alloc, and heap alloc are only there for historical reasons, and they pretty much chain through to RTL allocate heap, all of them, which resides in NTDLL. Now interrupt me if I'm going too fast here. Let's assume we have a program which allocates 2 blocks of 32 bytes each using the RTL allocate heap API. The memory will actually look like this. The first pointer to the first malloc, which is returned, like the return value of the first malloc, will be the beginning of memory block A, but not block A, which lies before the buffer that is returned. So we have some control data Windows uses internally in that gray field, block A control data. And then the second buffer is allocated, and again, we get the pointer to memory block B returned and a control block before that. Now assume we have one of those standard overflows where we can just overwrite a few bytes behind our original buffer, and we overwrite the entire block B control data. Now, if we manipulate this smartly or in an intelligent manner, we can get RTL free heap to write to arbitrary addresses. I'll start up a disassembly of NTDLL for that. Okay, now I know this looks scary. This is the disassembly provided by a very good disassembler from Belgium. If you disassemble the NTDLL and look at RTL allocate heap, I'll have a sip of water and then explain what's going on. Okay, this function takes 3 arguments: a handle to the heap where it's trying to free, some flags, and a pointer to the memory actually. We'll skip all this crap. This is standard function setup, pretty much. Go down a bit. Here we can see that it checks for a null pointer being supplied to free. If the pointer which it has supplied is in fact 0, it jumps here and returns true. So it doesn't do anything. Then it checks some flags in the heap which have to be specifically enabled using the gflags utility, so they're not really interesting. And then here, they load the ESI register with the pointer to our control block. EDX points to the buffer. EDX -1 is the pointer to the control block. So ESI gets loaded with it. And then they test field 5, which is in my slides called field 4, which is a bit of a bad naming convention. They test field 5 for its lowermost bit. So unless the lowermost bit of field 5 is set, they'll bail out an error and nothing will happen. So I'll advance the slides by one. Field 5 are these 8 bits for flags here. I called it 5 because it's at offset 5 of the structure. So the structure is 8 byte in total, and at offset 5 here, there's the 8-bit. So what they do here is they test whether the lowest bit of the flag is set. If not, they jump out and bail out. DL is a part of the pointer. This is not really interesting to us because this will never occur. And then they compare block, like the control blocks, field 4 to 40 hex. And if it's not below, they'll bail out an error as well. So if you overwrite the control block with all A's, nothing will happen. Because field 4, this one here, needs to be lower than 40, which means you'll probably have to override it with a number. Okay, skipping down a bit further. We see here, we want to actually get to the is larger block code. I'll explain later why. They test whether AL, which is our flags, has bit 8 set. That one must be set as well. Then they jump to this point here, where they check whether the heap is serialized and so on. Then they enter a critical section so they don't get any heap corruption on multi-threaded allocations and frees. And then we reach this point here, where they test field 5 for the 4th bit. And that one must be set as well. And then we jump here to the arbitrary memory override. Of course, this isn't named that way in the disassembly. I named it this way, but okay, ESI, which is the pointer to the beginning of the structure, is subtracted from with 24 bytes. So they're moving backwards to the previous buffer, save this in some local variable here. Then they load EAX from that location, which we have supplied because we've smashed the buffer, and the control structure in our buffer is buffer previous to the buffer we're freeing currently. That value gets saved in a local variable, and then the value at 4, like at an offset of 4, is loaded into ESI. It's saved into a local variable, and here we have an arbitrary memory override. We supply ESI, we supply EAX. We can write any value to any location. Looks a bit nicer, whoops, in the slides. Here we have the criteria which our block has to fulfill. Under Win2k, it's enough to overwrite the 8 bytes at the end of the buffer with XXXX, 99XX. Yes?
Do you have any idea what's the real use of that?
Basically, they're doing a lot of very complicated checking. Is the previous buffer free? Is it free and larger than something? If yes, then coalesce the two buffers. Basically, they're trying to prevent a fragmentation of the heap. Assuming that you have a lot of small allocations, and then you start freeing them, they have to check whether two blocks are next to each other and free. If they are, then they need to be put together so that a larger allocation can fill in that gap. Otherwise, you'll have the heap very badly fragmented. That doesn't mean that the heap can't get fragmented. A friend of mine is writing device drivers for mastering programs, and he actually had to implement his own kernel memory allocation routine, because the NT kernel memory allocation routine would crap out if you were allocating too many strangely sized buffers. It was pretty bad because the bug only occurred after some company in Asia had burned 50,000 not working CDs. He had a bad day. But well, well, if you want my advice, don't rely on computers. Okay, so to illustrate it again, we have memory block A, which we've overwritten, and we override the block B control data. And then we've put all the criteria, which I've mentioned before, in there, and ESI, instead of pointing to the beginning of block B, gets subtracted 24 and points in the middle of our buffer. And then they read EAX from there and ESI from there. At this point, we can write to any location in memory, any value that we wish to write. Any questions concerning this? Okay. So what we can safely claim is that if we can overwrite a complete control block, or at least the lower 6 bytes of it, and have control over the data 25 bytes before that location, we can easily write any value to any location in memory. Of course, neither the location nor the value may contain a null byte. If it was a string operation that smashed the buffer, but that doesn't need to be the case always, so it could be a memcopy override or whatever. And something that should be important, or is important, is that we've ignored a lot of other branches. I mean, we've jumped to a certain location in memory where the easiest way to get the override is happening. Now, there are other ways to override arbitrary memory, and depending on how much you're overriding and what you're overriding with and so on, it just takes a lot of creativity and time to look through NTDLL, and you'll probably find a way to write to arbitrary addresses. A friend of mine, Joey, who used to speak at Black Hat as well, has actually sent me a document a few weeks ago where he told me he has found ways of exploiting heap overruns. I looked at it and it was completely different from what I was doing. It worked, it exploited the same function, but he took a different branch. Now, I like to think that my solution is nicer than his, but in fact it isn't. It's just 2 ways of skinning a cat. So I think we should have a short demonstration showing this off. Okay, here we have a small example of vulnerable program. And in order to have it a bit more understandable for the audience, I'll compile it with, or I have compiled it with debug information, which will make it a bit more readable to those not very fluent in assembly. Which also means that we have some alignment issues that will, like normally we only need to read 30 bytes in here. And due to the debug information being put into the binary and the compiler acting differently, we actually have to support 112 minus 8, which is, I'm not good at math, bytes into there, and then we'll exploit it. But I think it should be fairly obvious. So we're allocating 2 blocks, then we issue a gets into the first buffer, and that should show us that we can overflow the buffer with anything we like. Okay, here we have the program in the debugger. We hit F9 here. Let the program run. And now, first we send ADAs. 80, 90, 100, 110, 112. Now here's the control block. We hit enter. We go into disassembly mode. This chains through to RTL3 heap. We have the standard setup. They test those strange flags. We load ESI with a pointer to the control block. They load AL with ESI plus 5, which is the supplied X. Oh no, 39 is the supplied 9, the second supplied 9. They test the lowest bit. They test ESI plus 4 for being below 40. We land here. They enter a critical section to make it safe for multi-threading. They test ESI plus 5 for bit 8, which is set. We land here. ESI points to our block. They subtract 24, 18 hex. We land here. They load EAX with the value we've supplied. They load ESI with the value we've supplied. And anybody can imagine what this does. It just moves the contents of the EAX register to the location pointed to at ESI. So if I let this run, there's going to be an exception. Just to demonstrate that regular stress testing wouldn't have found this, we go into the routine here, into an RTL3 heap, and we run through it. And one of the checks fail. They issue an error message, jump and return. So goodbye Retina, goodbye Perl. Actually, do you want me to write to some special address you supply, or do you believe me that this can be done with pretty much anything we supply? Okay, you tell me any value in, well, which can be easily entered right here now. So location underscore underscore, or value underscore 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 to location. I don't know. Okay. Now this should be 90, 100, 110, 112. RTL3 heap. Enter critical section. Load EAX with underscore 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 underscore. Load ESI with I. And write underscore 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 to I. That was one I too much. Any questions? Yes?
What's the use of the third buffer?
I think I used it in testing at some point. I never bothered to take it out. Hey, I don't write good code, I just point out other people's mistakes. Okay, for those of you not used to reading disassembly, we can have a short look. I wrote a small program that the disassembler can create call graphs, but they don't always work, especially not with weird code like NTDLL. So I've written myself a small plugin that creates a flow graph, which might be a tad easier to follow. So you have the entire block of initialization here, which we'll gladly ignore. You have the comparison if this is a null free here. If it's null free, it follows this branch down here and bails out. If not, we go here. It tests some weird flags, whether it wants to do a slow free or not. We don't want to do a slow free, or it never does a slow free. So we land here, where it loads the heap description block in EDX -8. and does the check whether the lowest bit of field 5 is set. And I'm wondering where the next error is heading to. Oh, it's heading down here. If it is 0, then it adds to error. In our case, it doesn't error. So it goes on to some more checks. It tests the L47. It checks whether the byte is below 40. Then we land at this point where we actually want to take this branch down here. I should start making colored graphs. I think black and white is kind of dull. Okay. And then they check for the bit 8. And it is set in our case, so we jump down here. To the enter critical section and to the arbitrary memory overwrite, which is down this branch. Those call graphs are not easy to navigate. And apparently there's no good graphing utility that can display very large graphs, because I was playing with pointer control flow graphs recently, and all the utilities I have crash after eating up all CPU power for about 20 minutes. It's a fairly large graph. I don't intend to be able to read it, but I would like to debug some code, and it seems there's nothing out there. Okay, I think we've pretty much covered NT here. So we'll move on to the Ball and C++ runtime library. And in Ball and C, we have a bit of a different situation. I'll quickly fire up the disassembly so we can look at it. Oops. So, here we go. Let's just assume that we have the same situation again, where we have memory block A and memory block B, and we override memory block A to override the control data of block B. Now, we can look a bit at the free handler in Ball and C's libc in the disassembly. Here we see that it checks for a null free, like for a free 0 again. If it's null, it bails out. This line loads the control block into EDX and then compares it to 1 megabyte. If it is lower, it jumps to small free down here. If it is larger, it jumps to the page deallocator, because if a very large memory block was allocated, it was not chopped off a small page, but it was multiple pages being served out to the application. So the large allocator here does not do anything of use. It just calls the virtual memory API, and they just deallocate the pages and don't mess with any structures in memory. So we can't really do anything here with assuming that we write a value larger than 1 megabyte to that control block. Now from this we can see that no matter what happens, if we completely smash B with data, then we're not going to get anywhere, because to completely smash B with the block B control block with data, we would be writing a value larger than 1 megabyte, and that would mean that nothing would happen. They would just call the page deallocator, and that would be it. So we actually want to have something like an off-by-1 exploit in heap memory here. If we look at the small free algorithm a bit, we can see that there's another check for a null free. Then they load the control block in ECX and do some tests on them. I'll quickly try to figure out what I was thinking when I was preparing this. Oh yeah, okay. Yes, okay. Actually, I think we have many ways here to override memory, but this is just one. Okay, now assuming that we have an off by 1, and we override the lowest order byte of the control block, then reach this code here. First it tests whether the pointer being passed to this routine was null. It then loads the value into ECX, like the control block into ECX, and tests whether bit 2 is set. Bit 2 is normally set, and it indicates that the previous block is in use. To those of you that have played with malloc overrides under Unix, this should be very familiar because Borland just copy and paste the GNU implementation. Anyways, that bit 2 in B's control block indicates A is not free. So if A is not free, they don't do much, they just bail out. So what we want it to do is we want it to think that block A is actually free. So as we have an off by 1 exploit here, we overwrite the lowest order byte of that control block with null. So when it tests bit 2 here, it actually jumps here because it thinks the previous block is free. And then it tries to coalesce the two blocks. So we land, it does some arbitrary checks here, zeroes out some bits, checks for some more flags. And down here, this comparison for some reason always passes. It seems to be some kind of debug implementation. And then we jump to the arbitrary memory override. Now, EDX is the pointer to our control block. So it reads the data at EDX plus 8, which is in memory block B, and reads the data at EDX plus 4, and then writes to ECX plus 4, which we have supplied if we control memory block B. It writes basically, well, it takes a value out of memory block B because it thinks it's free and expects some internal structure to be there, and writes to the pointer in that structure some data in that structure as well. And if we control memory block B as well, we can supply that entire structure. And as we've manipulated the internal logic of the free algorithm, it's pretty, well, we are manipulating it to think the structure was there when it wasn't, and we're supplying all pointers. So we can, again, write to any location in memory. I'll try to demonstrate that. It looks a bit more complicated, while in fact it's simpler than the NT allocator. It just has more weird offsets with plus something here. So oops. Okay, here we have this program. We allocate block A, we allocate block B, and we assume that we can supply data in both blocks. And then we call free here. We want to set a breakpoint on the free call here. 401A64. Somebody try to remember that number. Okay. Okay, this is the first 30-byte buffer we're going after. So 10, oops. 20, 30. Of course, all buffer sizes are rounded up to a 4-byte boundary, so we supply some extra nulls. Now we're at the end of the buffer, and now we can see that nothing will happen if we override this control block completely. I hit enter, and we enter the same stuff again in the next buffer. And here we have the free implementation of Borland. EAX is the pointer to the second buffer. EAX minus 4 is the control structure which we have overwritten with all A's. They zero out the lowest few bits, and then they compare it here to EDX. They compare EDX, which is the structure we've overwritten, like the value of it, to 1 megabyte. Our value is not below, so the page deallocator gets called, and nothing happens. Thump. So we only want to exploit, or to only write 1 byte extra. 30, 32, and that should be it. And the next buffer should contain our data. Okay, we're in the free again. We have this comparison here, and this time EDX is completely zeroed out as we've overwritten the lowest order byte, and it jumps to the small deallocator. It checks for the null. It adds -4 to get the control block. It loads it into ECX, tests whether the previous block is free. The previous block is not is free as we've set it. We've made it believe that it is free. So it jumps down here, does some manipulations, and finally lands here. We seem to have landed elsewhere than I claimed before, but we're landing in an arbitrary memory override. Anyways, these ones are to be ignored. It seems that something is going horribly wrong. Okay, we hit an exception, which is good. I'll just try to figure out what's going on. I think I made a mistake in my preparation. Gets weirder. I have to excuse myself. I'll need a few seconds to figure this one out. If anyone has any questions in the meantime, go ahead. Ah, crap. Yeah. Now you can see heap overruns are not always easy. It's been a while since I played with it and just looked at it yesterday evening again. Okay. Okay, now it works. I don't know what I did incorrectly the first time, but it seems that something unexpected happened which shouldn't have happened and which will most likely not happen again. Okay, we have the null byte we write to after the end of the buffer. We write some data into this buffer as well. And here we go. We pass the comparison concerning the size. Move down here. And then at this point, EDX points to the beginning of our buffer. And now EBX is loaded with the value there. ECX is loaded with the value in buffer B as well, namely the value at offset null, like the very first value. Okay? So we can see that we've supplied EBX as it was at offset 4 in the buffer B, and we've supplied ECX as it was at offset null in buffer B. And what's happening now is he's writing a value to ECX plus 8, and that value has been supplied by us. We have supplied ECX, And we've supplied EBX. So again, we can write an arbitrary value to an arbitrary location. I'm sorry if I confused you a bit with me fumbling around here. I'm not quite sure what happened, but I might have just made a stupid typo or whatever. It led us to the wrong location. I assume that as you didn't believe me that this works with heap overruns under NT, you don't believe me that this works either, so I have to demonstrate it again.
If you're proving that you thinking block A is already free, so it's less than that, why does it think it's a control structure in block B if that's one that you're free?
Actually, I think we're making it believe that block B is free. Or aren't we?
Because you smashed the control block for B.
It's true.
And then you free B.
And then we free B, apparently. Let me ponder this for a second. To be honest, I never asked the why, I asked the how. Now, this might be a bit strange because most people dealing with the source side of exploiting heap overruns are actually understanding the entire thing. But if you look at the NT heap allocator and you have the choice of either spending 10 hours figuring out how to exploit it, or spending 60 hours understanding why the hell it does what it does, which way do you choose? So I have to admit I have no idea why this is going on. Just plain simple. But I can assure you that if any one of us sits down and looks at the disassembly for a few more days, then we'll know it. But who wants to know? I mean, this is not about heap management, this is about heap abuse. But yes, I got caught with my pants down. Okay. I just quickly show that we can write to any location. Now, which location do we choose? Underscore, 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 underscore plus 8. Let's look at the disassembly whether it's actually true. The memory override happens here. EDX plus 8 is the value, and EDX plus 4 plus 8 is the location. Okay. So the value is I, and the program will add 8 to the underscore, 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 underscore down here. So we'll not be actually writing to underscore, 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 but to underscore, underscore, underscore plus 8, which I think is all right to be classified as arbitrary. Okay? Now let's hope it doesn't take any unexpected branches again. Okay, here we go. EBX is loaded with, I made a mistake. I told you this was not going to be smooth. I promise to be better in the second half, if you're still here then. Okay, now let's do it like this. Okay. I'm completely lost. We'll eventually get there. I mean, we still got plenty of time, that way I can hide that I don't have enough stuff for the first half. Yes, and the third byte should be... it seems to read at... It seems to read at this location plus 4 and plus 8. Yeah. So let's see what happens here. Passes the check concerning the size, all right. Jumps into this part. jumps down here, does the compare, jumps here, and EDX is not pointing where we expected it to point for some silly reason. We still get the exception. Okay. We pass this part. We make it believe that the structure was empty. Jump down here. Okay, I think this is not working at all. Now, I promise you, I'll tell you how this works in the second half. We get an exception. It worked during preparation. It doesn't work now. We all know how computers are. All right. So I think I explained this before in the debugger and the disassemble what I have in mind with what doesn't work currently. We have the buffer which we overrun. We write a null byte to the control structure, and we control the next buffer as well, which leads to data being read from the next buffer and actually leading to an arbitrary memory overwrite. So to sum things up is, I feel like a complete cheat right now, but I promise I'll do it in the second half. All right, we've shown, at least for Windows 2K, not for Ball and C yet, that we can override heap control structures and thus write to an arbitrary location in memory. And to sum things up concerning exploits and buffer overruns in general is that stack-based overflows are slowly being hunted to near extinction, and that easy-to-spot bugs are slowly being weeded out, and the hard-to-spot bugs are the ones that are still left. And something that's interesting about heap bugs is that with the advance of object-oriented programming and STL and so on, we will be seeing less and less stack-based bugs or stack-based overflows, because people just don't use the char buffer 20 anymore, but they use some class with an internal buffer where they memcopy into or whatever. And if we're going to have overflows in the OOP world, then it's going to be heap overwrites. It's not going to be the stack smash. Furthermore, even in STL and even with C++ and OOP and everything, off-by-ones are possible. Not necessarily with a null byte, but just imagine an iterator going too far and so on. So some people claim that bugs will go away with new programming paradigms, but they're here to stay. And the elusive nature of heap overruns will basically, well, make the tools Retina, Fuzz, all the Perl scripts and so on obsolete. Because the future is heap bugs and they can't be found using stress testing, but only with source or binary analysis. Reverse engineers, if they don't scrub as I do, are at an advantage. They can understand and document the compiler. If you have a compiler, I don't know whether the vendor of the compiler will give you the source to the libc and the source to the heap allocation, and you can bet that Oracle will not give you the source for their heap implementation, and you can bet that Netscape will not give you the source for their heap implementation either. So unless you're a bit used to reading disassembly, you don't really know what to do and how to do it. Furthermore, there's a lot of bugs in the compiler themselves which we're dealing with in the future, I think. If you look at Ball and C, for example, we've seen that they need control structures for controlling their blocks. So when you allocate a certain amount of memory, they actually need 4 bytes more because they need the size for the control structure as well. And what they do is they take the value of what you put in there, the amount of memory you want, and then they add the control block size, and then they allocate that. Now assume you request a memory block of a bit like 4 gigabyte size, -2. They add 4, it wraps around to positive, and they allocate you 4 bytes and return it. And there's no error message. So compiler bugs are really going to screw programmers over badly. And especially in the embedded world, there's a lot of bad compilers. And while we're at it, Java is claimed to be secure, but after I've done a survey over buggy compilers during the past few months when it came to C compilers, I'm not really sure that the Java runtimes or the Java compilers are any better. And even then, if the language is working correctly and has strong type checking and so on, there are logic bugs everywhere that can go insanely wrong, and programmers don't read specifications. A nice example I like to bring up at this point is usually that how many C programmers you know that can answer the following question? If you compare a signed to an unsigned value, like is the unsigned value A smaller than the signed value B, what comparison will the what sign will the comparison have? Will it be an unsigned or a signed comparison? Unsigned. Unsigned A smaller than signed B? You had a good chance there. Now, has anyone ever bothered to read the specification, what the specification says, because it's a clearly defined state? No, actually I did. And the right side of the comparison dictates the signedness. So unsigned A smaller than signed B will have a different result than signed B greater than unsigned A. If you think those bugs are going away with new OOP classes, you're wrong. Just plain wrong. Okay, something else that I mentioned is that our heap bugs are not actually taking control over EIP directly anymore. And as we see more and more advances towards the prevention of buffer overruns like non-executable heap pages, stack guard, and so on, at least to prevent the stack-based overflows which execute code, and we have ways of making pages readable but non-executable, we can kiss our shellcodes goodbye. It's just a matter of time, but with IA64, people will start making all heap pages, all stack pages non-executable, and any user supply data will not be able to execute. So with the heap bugs, we are already demonstrating the future of bugs. We're manipulating the internal logic of a program. We're manipulating structures it uses to store its own data, and then make the program do evil things. Now the simplest example is overflowing a buffer, and right behind your buffer there's a boolean is authenticated. That would be the easy way, or we do it like this. We're manipulating the compiler to do something which we want, which is not smashing the stack. So we can safely assume that in the future we'll have to have more of a program understanding to actually do anything useful, because we're manipulating the way its logic works. We're not just smash the stack, put in the shellcode, execute bin sh, and we're in. We'll have to play with how the thing works. All right. Yeah, I'm trying to brag a bit at the bottom that reverse engineers are useful, but after we've seen how I fumbled, I'll just skip that part. And I think we're pretty much scheduled to have a break right now, aren't we? Right. Thanks, and I'll try to figure out what went wrong for the second half. Any questions concerning this so far? Yes, please. For what? The question is whether you can scan binary code to find buffer overruns. Well, they are overruns in a way. I mean, they're overrunning the malloc buffer. So yes, you can. I'm actually holding a training class on that, or I held a training class on that on Monday, where basically you analyze the binary and read the disassembly and scan for commonly misused library functions and how they might overwrite stuff. But you cannot simply scan the binary for an arbitrary memory override in general, because there's a lot of writing and reading in an application normally. And if you just scan for the instructions overriding arbitrary memory, you'll get about every 8th or 9th instruction will be one. And if you look at the common disassembly consisting of a few million, you can grow old looking whether you can do anything useful with them. Any other questions? All right, then, have a good break. Thanks.